All right, today we're talking about Chapter 2, Section 2, solving multi-step linear equations. So solving multi-step linear equations, we're going to be solving equations of the form ax plus b is equal to c. You might be familiar with ax plus b equal to c, but we'll probably touch on that later whenever we do actually get there. All right, but in Section 2.1, the equations we learned to solve are in one of two forms, x plus b or ax is equal to c. In the first type, the coefficient of the variable of x was always plus 1, and we use the addition principle to add or subtract constants to solve the equation. In the second type, we use multiplication principle or division principle. We did division to multiply both sides of the reciprocal of the coefficient of the variable or divide both sides by the coefficient itself. All right, so now we are going to apply both of these techniques in solving equations of the form ax plus b is equal to c. Okay, so now we're combining pretty much everything we did in 2.1 into a nice equation. And again, here's a procedure, but we're not going to go over that. It's there for you if you need it. Instead, you get the best procedure of all. Hearing me talk through it. Okay. So we have 3x plus 3 is equal to negative 18. So we know what we need to do is we need to isolate the x. Okay. Well, the easiest way to do this now is we need to add and subtract everything away from whatever the variable x is before we do anything. And it looks like right away we can subtract 3 from both sides. And by subtracting 3 from both sides, I'll end up with a 3x is equal to a negative 21. Okay. Now the x is kind of by itself. All right. The easy part's done. I would say, yeah, it's the easy part. Next, what we're going to do is we're going to have to divide both sides by a 3 because we need to isolate the x all by itself now. Okay. And by isolating the x all by itself with 3x over 3, you know, 3's cancel, so we have x. And what is negative 21 divided by 3? Well, negative 21, I'm sorry, 21 divided by 3 is 7. Then we have a negative in front of it, so we have a negative 7. Okay. And just check your solutions. Right. At this point, all I'm doing when I check the solutions is just kind of is a redundancy in a lecture, and I don't necessarily think it's needed, especially after we did it all in chapter 2, section 1. But all we do again, we just put the negative 7 in, right? And we can do this mental math pretty fast. So 3 times negative 7 is a negative 21. Negative 21 plus 3 is a negative 18, and we do indeed have negative 18 is equal to negative 18. Okay. But moving forward in the lecture, I'm probably just not going to do that because it's just a redundancy. However, for you as a student, it's very wise until you just get super good at this to always 100% of the time check your work. All right, so we've got we'll write all well. We're gonna kind of write this with combined terms already here. Okay, so negative 26 by itself on the left was good to go. On the right, though, we have a 2y and a minus 4y. Okay, so let's just go ahead and combine those like terms. So we have a negative 2y and then minus 14. Okay, so what do I need to do here? Well, I need to get the 14. I need to get the 14 from the right side to the left side. So what do I do? I need to add 14, right? So if I add 14, let's go ahead and do that. Add 14, that goes away. If we add 14 here, well, a negative 26 and a positive 14 gives me a negative 12. Negative 12 is equal to a negative 2y. And then from here, we need to divide by a negative 2, right? So divide by negative 2, divide by negative 2. Well, what is negative 12 divided by negative 2? Well, 12 divided by 2 is 6. And then we have a negative over a negative, so we have a 6 over here. And that's equal to, well, a negative 2 divided by negative 2. The whole point of that was to isolate the y, so we have a 6 is equal to, I'm sorry, 6 is equal to y. I've been really stopped up lately. I'm sorry. Decimals. Ugh. Okay. So I'm gonna probably have to bust out my calculator for this. Okay. Actually, not really. So 16.5. I'm gonna combine the like terms on my left side. 16.53 minus, and again, just doing like terms here. Okay. Well, 0.53 minus 0.23 is equal to a 0.3, and that subtracts 6. So I'm going to have a 10.3 on the left minus 18.2z, and that's equal to a 1.2. Okay. Uh, and again, all we have to do is just begin by isolating the z and get things done. So we're going to subtract 10.3 from both sides. So we're going to end up with a, let's see, we did it this way. Nice. 10.3, that's gone, minus 10.3. And then we're going to have, we're going to end up with a negative 18.2z, and that's equal to 1.2 and 10.3 is 9.1, so a negative 9.1, right? Negative 9.1. And then we're going to divide both sides by negative 18.2. Okay, so we're going to divide both these sides by negative 18.2 and divided by negative 18.2. And this should be pretty obvious. 9.1 is indeed half of 18.2. So we're going to end up with z is equal to just simply 1 half. Okay, or if we did it in decimals, 0.5. Ugh, fractions. Ugh. Right. So what we're going to do here is we're going to find what the least common denominator, or least common multiple is, I guess, least common multiple of 6, 2, and 9. Okay, well, what is the smallest number that 6, 2, and 9 will go into? Right? It takes a little bit of thinking here, but I'm pretty sure it's going to be 18. Right? 6 goes in 18, 2 goes in 18, and 9 goes in 18. So what I'm going to do, right, so 5, 6x minus 5 halves is negative 10 over 9. Okay. So what I'm going to do, since I know that is my least common multiple, is I'm going to multiply this entire problem by that number, 18. Okay, and again, the number 18 is just the smallest number all three of these will go into. And the reason why is because what it's going to do is it's going to clear the fractions. Right? Now we pick the smallest number. There are an infinite amount of numbers that will work, but we're going to pick the smallest number because dealing with doing arithmetic with small numbers is a lot easier than dealing with arithmetic with larger numbers, right? I mean, we could have chose 180, but I don't feel like multiplying things by 180. Multiplying by 18 is much easier. So if we distribute here, okay, right? Well, the 18, and the 6, right? This turns to a 3. That 6 turns to a 1. So 3 times 5 is just 15. So we'll end up with a 15. We'll have a 15x right here. Okay. And then we'd multiply over here again. Okay. Well, this 2 turns to a 1. This 8 turns to a 9. And then 9 times 5 is 45. So we have a minus 45. And then we distribute here. This 9 turns to a 1. This 8 turns to a 2. 2 times 10 is 20. So we end up with is equal to a negative 20. Okay. And from here, it just becomes one of the easy problems that we did in the first examples. This is actually pretty interesting. I was looking over here, and I'm going to go and snip it. I think it's interesting. Alrighty, so here we go again. So solve equations of the form ax plus b is equal to cx plus d. Okay, so now we're getting a little more complex. All right, so now we're going to be having our variables on both sides of the equation, right? And the thing is, it's solved exactly like you think it would be. Right? You know how we have been combining like terms? Well, we're just going to continue that process of combining like terms, except now we're going to put the variables on one side as well. Alrighty, so let's go and write this whole thing out. We need to get the x's on one side, and we have to get the constants on one side. Okay, and most of the time it's pretty easy which side you think you should get the x's on, because for me personally, I like to make sure that my x's are positive. And what I mean by that is, if I subtracted 5x from both sides, well, there would be no x on the left side, but we'd have a negative 3x on the right side, and I don't really want to deal with I don't really want to deal with a negative. Okay, so instead, what I'm going to do is I'm going to subtract 2x from both sides. So here's what we're going to do. We're going to say minus 2x here. That's gone. Then minus 2x over here. That means that gets 3x. Right? We're going to subtract 3 from this side, and then we're going to subtract 3 from this side. So negative 18 minus 3 is equal to a negative 21. And that's my problem so far. All right, and then again, what I do is I divide both sides by 3. So divide by 3, divide by 3. I end up with x is equal to a negative 7. Okay. Not so bad, and very super duper colorful. I like that. Let's do it again. So let's go ahead and rewrite this. We're going to say 4x. Actually, we can combine like these like terms already. So if I read this out, it's 4x plus 1 minus x. Well, I can combine the 4x minus x, so I'll have a 3x and then plus 1. That's equal to, on the right side, a 2x, and then I have a minus 13 and a positive 5, so it's going to be a negative 8. Okay. So let's go ahead and begin the process now. So we're going to subtract 2x from over here, subtract 2x over here. That gives me an x. Going to subtract 1, that cancels that. Subtract 1, that gives me a negative 9. And that, that was it. Negative 9, yeah. No need to do any division or anything like that. We just get there. Okay. So hopefully you just kind of see the process here. Um, it's not terrible. It does get very tedious, especially towards the end of this semester. You do it again in your next math course. It gets very tedious. But as far as grades go, I feel like it's a pretty easy grade. So 6y. So this time we're going to be subtracting 6y from the left side. Looks like. Okay. So previously I did say that I want to make sure that my variable is positive, and I'm going to continue that this time, right? So I look at my 7y, I look at my 6y. Well, my 7 is larger. So what I'm going to do is I'm going to subtract 6y. Okay, so I'm going to be putting my variable on the right side now. And then I'm going to add 3.6. I'm going to add 3.6. That's 5, 6.1. Okay. And then I've got y is equal to a 6.1. More fractions. Okay, let's see if we can't combine like terms real quick. It looks like we can't. Okay, so we can't combine like terms, but here's what we're gonna do. We're going to. I don't know if the book does it as well. Yeah, we're just gonna get rid of the fractions before we even start moving x's to one side. Okay, so that's good. So let's go ahead and look at our denominators here. We have a 3, we have a 5. I'm sorry, we have 15, and we have a 5. Okay, what is the smallest number that those three can go into. What is the smallest number those three numbers are going to? All right, well, it looks like 15 is, right? 3 goes into 15, 15 goes into 15, and 5 goes into 15. So that's the smallest number that we can go into. So what I'm going to do, I'm going to take my equation, and I'm going to multiply the whole dang thing by 15. Okay, so let's distribute. Right? So I got 15 over 3. 15 over 3 is 5, so I got 5x. 15 over here, the 15's cancel, so I end up with a 13. Distribute here. Let's do a different color. Distribute here. The 5 turns to a 1, this turns to a 3, and then 3 times this 3 is 9, so we got 9x. And then we do the last one here. It's just 15. 15 times negative 1 is negative 15. Okay. And that's it. And then it just becomes a problem that we have seen before. Ooh, oh man. Okay, so now we're getting into the super duper tedious stuff. This is a winner right here. Okay, so what we're gonna have to do is we're gonna have to deal with these parentheses, right? PEMDAS. So we're gonna have to deal with the parentheses before we even begin the process of doing the computation here. And since it's written a little small and I like to draw my arrows, I'm gonna rewrite this. Okay. So we have a negative 2 times a positive 5x. So that's going to be a negative 10x. So negative 10x. And negative 2 times a positive 13. So it's going to be a minus 26. And then this negative 2 just comes on down. And then we're going to have a negative 6 times a 3x. We have a negative 18x. And then negative 6 times a negative 2, which is going to be a positive 12. And then minus 41. So now we need to combine like terms on each side. So on the left side, it looks like we just have a constant that we need to combine. So the left side just becomes a negative 10x. And then we have a negative 26 and negative 2, so it's going to be minus 28. And that is equal to, on the right side, looks like we just have a negative 18x. And then we combine the 12 and the 41, so we get a negative 29. Okay. And again, at this point, it just becomes the exact same type of problem that we have dealt with in the first 7 examples of this text. Alright, so conditional equations, identities, and contradictions. This is pretty important. Right? So in solving equations, there are times when we are concerned with the number of solutions that an equation has. If an equation has a finite number of solutions, that is, the number of solutions is a countable number, the equation is said to be a conditional equation. As stated earlier, every linear equation has exactly one solution. Thus, every linear equation is a conditional equation, right? Because 1 is indeed a finite number, so linear equations are conditional equations. However, in some cases, simplifying an equation will lead to a statement that is always true, such as 0 is equal to 0, right? That is always going to be a true statement. We would get something like this, 0 is equal to 0, on some of the computation problems that we do. I can't remember if we do them in this section or not, but when we see them, I will definitely point them out. In these cases, the original equation is called an identity and has an infinite number of solutions, which can be written as all real numbers. Again, that funny R that we talked about before. If the equation simplifies to a statement that is never true, such as 0 is equal to 2, and again, something we'll probably, I guess we'll see in this section, then the original equation is called a contradiction and there is no solution. Okay, so let's go ahead and see what we're talking about here. And that's not it. Yeah. Okay. So, uh, example 11 is exactly like what we have been doing. It's just more of the same. And I guess I'll just go ahead and do it. It's not going to kill me. Um, let's go ahead and write this in distributed form. So we're going to have a 3x plus 15 plus 1 is equal to a negative 11. Okay, we're going to combine the like terms on the left, so we're going to end up have a 3x plus 16 is equal to negative 11. Okay, we're going to subtract 16 from both sides, so we're going to end up with a 3x is equal to a negative 28. I'm sorry, negative 27. Sorry about that, negative 27. And then we're going to divide both sides by 3, so we're going to end up with an x is equal to a negative 9. Okay, this is a conditional equation. The problem reads, determine whether the equation is conditional, identity, or contradiction. Well, we have one solution. One is a finite number, and therefore this is going to be a conditional equation. Okay. The next example is going to be an example of a those. Okay, next example is going to be an example of a contradiction. Okay, so let's begin this process here. We're just going to go ahead and distribute this. So if I distribute through, it's going to be a 3x and then minus 75. That's equal to, I'm sorry, not equal to, plus 3x, and that's equal to, distribute the 6 through, so it's going to be 6x plus 60. Okay, so let's start this. On the left side, I can combine my 3x's, so I'll have a 6x minus 75. That's equal to 6x plus 60. Okay. Let's get the x's on both sides. So I'm going to subtract 6x. It looks like I'm just going to subtract 6x from the right side. So let's see what that looks like. So we're going to say minus 6x. That's gone. Minus 6x. Okay, well we have a problem here. 6x minus 6x, well that makes that gone as well, right? So I have negative 75 is equal to a 60. Okay, is negative 65 equal to 60? No. Okay, therefore this is called a contradiction, right? This is never true, and you can really spot why that is the case by looking at this line right here. We have 6x minus 75 and 6x plus 60. Okay, there is no value that you can plug in there for x that would make that a true statement because one is minus 75 and one is plus 60. They're completely different. What the operation that you're doing after you multiply by 6. So that's how we can just kind of see how we can tell that yes, this is indeed a contradiction. This equation should never exist, right? Because there's just no solution to it. It's a contradiction. There's nothing that you could ever plug in that would make that equation work. That's an example of a contradiction. And then lastly, we're going to have an example of an identity. Okay, so this reads, determine whether the equation negative 2 is conditional. Okay, so let's go ahead and do the distribution here. So we have a negative 2x plus 14 plus x is equal to a 14 minus x. All right, now again, all I did here is I distributed right away. So let's combine like terms on the left side here. We have a negative 2x and a positive x. So we have a negative x and then plus 14. And I have is equal to a 14 minus x. So hopefully you can kind of see what we're looking at here. Notice how this is pretty much the exact same thing as this, right? It's just rearranged. I have the 14 in the front and the x in the back, as opposed to the left side, I have the x in the front and the 14 in the back. But let's proceed. Okay. Well, let's go ahead and add x's to both sides. I want to have my x's on the right side. So I'm going to say, I'm sorry, I want to have my x on the left side. So I'm going to say plus x, that's gone. Plus, oh, so kind of same situation on the previous page, okay? But this time, it's not that we're going to have a contradiction, because what remains is 14 is equal to 14. And since that is always a true statement, since 14 is always equal to 14, then this problem is going to have an infinite amount of solutions. Okay, we call that an identity. And again, like I said, you could really see that point driven home looking right on this line right here, that the left side is the exact same thing as the right side. Okay, and that concludes today's lecture.